And I will again repeat, you have 2 weeks until the first exam. Make sure that you have an access to my MATLAB because the exam will be on the Pearson. And I have already assigned your second homework. I have postponed the date for the first homework because you are just buying the book and maybe you need some more time. And we are done with the first order differential equations. We talk about linear differential equations, constant coefficient or variable coefficient. We talked about separable equations. We were able to solve some nonlinear ones even. And we talked about exact equations. We talked about autonomous equations and different equilibrium values, stable, unstable, or semi-stable. We talked about Euler method. If we cannot find the analytic solution, how can we find the approximate solution or numerical solution? And Euler method was one of them. And these kind of things, we are done with the first section of this class. We talked about how we can model the dynamics. So you will be responsible, all of them, and also the second order one, you will be responsible for the first midterm. Now I will share the lecture notes with you. Second order, linear, homogeneous equations, constant coefficients. Then I will start right now if you don't have any question. So far we were talking about first order differential equations. And you know what is first order. The highest derivative inside the equation is the first derivative. And once we say second order, now we have terms that has second derivatives inside our equations. And for this kind of equations, the general form is like that. The second order can depend on the independent variable, y, dependent variable, and the derivative of dependent variable. And it is linear if, again, you know what is the form of the linear equation. The derivatives are coming along and the coefficients can only depend on t and there is no restriction on t. And if this is not the case, you will have non-linear second order differential equation. But in this section, we will focus on the linear ones. A second order linear equation, this is the very general form. There is one coefficient that depends on t, y second derivative, qt, y first derivative, rt, y equals g of t. If your equation has a term that only depends on t or constant, your equation is non-homogeneous. If it doesn't have any gt term, it will be homogeneous. So if gt is 0, it is homogeneous. If not, it is non-homogeneous. Okay, and the solutions are different. We will be talking about the homogeneous case first. Non-homogeneous case, we will talk it later. We will call them different solution. Okay. So again, the focus of this part is homogeneous equation and in particular with constant coefficients. So in this part, we will be talking about this kind of differential equations. As you can see, A, B, C are just constants. There is no t coefficients. And initial conditions, since we are talking about second order derivative, we need two initial conditions because we need to find A, B, and C, three unknowns. And for them, we are going to be using the initial at y and initial at the derivative of y. So there will be two initials are given. One of them is in the normal y, one of them is going to be in the derivative. And our solution is going to pass through the t0, y0, and the slope of the solution, t0, y0, which is y0, y derivative. Let's look at this one. Y second derivative equals y equals 0. So as you can see, it is linear. There is no y first derivative term. The coefficient is 0, it seems. And our coefficients are 1 and -1. So you can write two solutions of this equation, e to the t. Try that. You know that if this function is a solution, you need to take the necessary derivatives plugged in. And if it is 0, these are the solutions. So the derivative of e to the t, first derivative, second derivative, and derivative, it will be all e to the t. So e to the t minus e to the t, 0. Exactly, this is the solution. And look at that. This is also the solution. So because negative e to the t minus plus e to the negative t, it will be also 0. This is the solution. And you will see that these are all solutions. And based on these observations, you can see that there are infinitely many solutions and they are all coming as an exponential form. So our solution is in this form. C1 e to the t, C2 e to the minus t. And exactly we will see that all solutions of the constant coefficient second order differential equations can be expressed as the linear combination of exponential solutions. Okay? So we will be looking for the solution that has an exponential form. And if the initial conditions are given like that, you need to put t at the solution. Once you plugged in t here, e to the 0 is 1, c1 plus e to the minus 0 is 1, c1 plus c2 equals 2, and also you need to take derivative of that one. Derivative of that one is what? c1 e to the t, negative is going down, minus c2 e to the t. And if you plugged in 0 at this one, you will have C1 minus C2, which is going to be negative 1. And you need to solve this system. You have two variables, two unknowns, and two equations. So you can solve that. You can add these equations. 2C1 equals 1, C1 equals 1 over 2. If C1 is 1 over 2, plugged in one of these equations, you will see that C2 will be 3 over 2. And once you plug it inside the general form of your equation, you can find the solution of your initial value problem like that. Okay? So the general idea is we are looking for exponential solution. But how can we know if it is going to be e to the t or e to the 2t or e to the 3t or what is the coefficient of t? I will come to that a little bit later. And for the solution, look at that. This is the graph of your solution. And this is the graph of the derivative of the solution. What was your initial at 0 at the y? When t is 0, y is 2. As you can see, the solution is passing through y equals 2. And in the derivative, what was that? When t is 0, y should be negative 1. As you can see, it is passing through negative 1. So the equation itself and the derivative has to satisfy the given initial conditions. Once you solve it, and you can see the curves in here, they are both true for both initial conditions. Now let's generalize it. We have second order differential equation in that form. You can see that here, second derivative, first derivative and y itself, and this is homogeneous. The right hand side is 0. And we are looking for a solution in the exponential form. So we want the solution y equals e to the rt. Let's say that. And if that's the solution, let's take the necessary derivatives, put it inside our equation, make it equal to 0. And the first derivative of e to the rt, r times e to the rt. The second one, r square, r times r times r square, e to the rt. And a times r square e to the rt. That's once I plug the second derivative of y in here. And first derivative again, r e to the rt. I just put it in here instead of y derivative. And y, it is given e to the rt is 0. So I have this equation. And if I factor out exponential function, because these are common in each term, I will have ar squared plus br plus c. So it's just the second order quadratic equation. And if that's 0, since exponential cannot be 0, the second order equation will be 0. And this equation is called the characteristic equation of our differential equation. Okay? So we need to solve this one. And you know how to solve it. Quadratic formula. Minus b plus or minus square root of b square minus 4ac over 2a, right? From there, you can find the roots of this second order polynomial easily. And for any constant coefficient homogeneous linear differential, second order linear differential equation, you can directly write the characteristic equation as AR squared plus BR plus C equals 0. Solve them. Put instead of R whatever the roots you found there. Okay, and these are gonna form your solution. Again, we have that one as a characteristic equation. Once we solve this with the quadratic formula, as I told you here, minus b plus or minus, here you go. Once you solve them, you can find two different roots. There are three possibilities. One of them is you can find two different roots like that. Or you can find two roots that is equal to each other, which means that you can find one root. Or you can find complex roots. And the solution of your differential equation is going to be changing according to what kind of roots you have. Okay? And in this part, let's start with if you have two different roots, the first choice. Okay? If you have two different roots, your general solution will be in that way. The linear combination of these exponential solutions, C1 e to the R1t plus C2 R2t. And this is coming from the superposition principle, and I will talk about it a little bit later. Now, any question? No question seems. Okay, let me continue then. This is what we said. So once you plugged in the initial conditions for the general solution, so you need to apply it at y, and you need to take the derivative of this y and apply it again, and you will find C1 and C2. You don't have to memorize this. You just need to know how to apply the initial conditions. You need to apply it in that one, and you need to take the derivative of that one, which is C1 R1 e to the R1t plus C2 R2 e to the R2t, right? And let's solve this linear differential equation. As you can see, this is second order. Coefficients are constant, homogeneous, right-hand side is 0. So I know that my solution isn't going to be like the exponential form, like that form. And if I plugged in this one, I can get the characteristic equation, which is r squared plus 5r plus 6 equals 0. And I know how to solve this one. Either you can factor out as r plus 2, r plus 3, or you can use the quadratic formula just as I shown in here. So once you factor it out, you know that the roots are minus 2, minus 3. If the roots are minus 2, minus 3, we know that our general solution is in that form. C1 e to the first root t plus C2 e to the second root t. So the first root is minus 2, the second root is minus 3, C1 e to the minus 2t plus C2 e to the 3t. This is the general solution of your differential equation. As you can see, it is so easy. Just write the characteristic equation, find the roots, put them as the power of exponential. Okay? And now, let's say the initial conditions are given. And you already found the solution is in that form, but you need also the derivative of your solution. So take the first derivative. The derivative of e to the minus 2t, the power goes down, which will be minus 2 c1 e to the minus 2t, and here minus 3 c2 e to the minus 3t. Here you go. You have the solution, the derivative of the solution. What you need to do is just plug in 0 for the first one, make it equal to 2. Plugged in 0 for the second equation, make it equal to 3. And let's do that. E to the 0, 1. So we have C1 plus C2 equals, it should be 2. There is a mistake in written, sorry. And minus 2 C1 minus 3 C2 should be 3. And if that's the case, you can see that C1 and C2 is like that. And let me see if minus C. Yes. And you can find the solution, as you can see in here, as an exponential form. So your solutions are not linear, and we solve in the Euler's method. To find the solutions approximately, it will be good at the beginning, but since our solutions is going it's non-linear, the error is gonna increase with time. Okay. So that should be, sorry, 1. Let me change the mistake in that one. This should be 1. Just to make sure that, wrong button. I changed it, so C1 plus C2 should be 1. I changed this initial condition. I typed in wrong, it seems. Okay. And another one. Here you go. We have the second order differential equation. Initial conditions are given. And we know that our solution is in the exponential form. So if I plugged in the exponential form, I know that my characteristic equation will be AR squared plus BR plus C. So 4R squared minus 8R plus 3 is 0. And this is factorable. You can factor this one as 2R minus 3 or times 2R minus 1. Or what you can do, you can use the quadratic formula just to make sure that. And you have two different roots. If you have two different roots, you are just putting this as the power of an exponential, and you can write your general solution as a linear combination of these two exponential. And now you know how to apply your initial condition. Plugged in 0 for t, make it equal to 2. Take the derivative of your solution, plugged in 0 for t, make it equal to 1 over 2. And you will find C1 and C2, and just plugged in here, and you can plot it in MATLAB easily. Any question? Did you understand if you have two different roots, how we are solving it? No question. Okay. Then I will continue with the existence and uniqueness. I will take 2 minutes. I need to bring some water. I'm coming after that. Here I am. Let's continue. I will share. I did not share. Here we go. Lecture. So if we have two different roots, we are just putting as the power of an exponential, and we are writing as the linear combination of two exponential solutions. That's it. And you know that from the first section, we talked about the existence and uniqueness. How can we make sure that the solution is exist in the given in some region that your initial is in, T0 is in. And in here, you need to check that where P and Q and G is continuous. Once you know the continuity regions for these three functions, you need to choose the one that T0 is in, okay? The idea is similar. We can generalize it for the nth order even. So let's say that this is our differential equation. This is linear, but it's not constant coefficient. As you can see, it is variable coefficient. And to be able to check the existence and uniqueness of these solutions, we need to put this one into a standard form by making the highest order derivatives coefficient 1. That's why we are dividing the equation by t squared minus 3t. Once we do that, we have P of Pt, which is t over, t is gone, so 1 over t minus 3, Qt, which is t plus 3 over t squared minus 3t. And these are, since g is 0, it will be 0. So these three functions, and we need to know where these functions are continuous. And these are rational functions, so we need to check the points that the denominator is 0. For p of t, it is 3. For q of t, it is 0 and 3. And this is continuous everywhere. So the only discontinuity points are 0 and 3. So I'm taking these ones out from the real numbers. We will have minus infinity to 0, 0 to 3, 3 to infinity. And where is our initial? It is defined at 1. And where in these regions, where was the regions? Minus infinity to 0, 0 to 3, 3 to infinity. And we are going to be choosing the one that 1 is. And you know that 1 is in the region at 0 to 3. So you can say that this initial value problem has a unique solution for sure, according to this theorem. Okay? And as I told you, we are writing the solution as the linear combination of two exponentials according to the principle of superposition. So once you find that, and this is going to be all true for if you have the same root, if you have complex conjugate root, we are using the same principle. So all linear combinations of these two functions, the two solutions, will be the solution of your differential equation. And all solutions can be written in this way. To be able to say that, we need also to check Wronskian. Okay. And what is Wronskian? Wronskian is, you should check that the Wronskian cannot be 0, because once you plug in these inside your equation, you will see that C1 and C2 in the denominator, it is coming this determinant. And since these are in the denominator, this cannot be 0. And you can make sure that Wronskian should not be 0 to be able to say that these solutions are going to form your fundamental set of solutions. And what is Wronskian? Here, you need to check the determinant of solutions you are writing and the derivative of solutions. Check the determinant, and this should not be 0. And you can say that for constant coefficient case, all the distinct ones and repeated ones or complex conjugate ones, the Wronskian is not 0. So we can generalize it. If we have a second order linear differential equation in that form, the solution can be written as the linear combination of y1 and y2 according to the superposition principle. Where was that? Yes, like that. And if the Wronskian is not 0, okay? This is going to be the solution, general solution of your initial value problem if the Wronskian is not 0. And as I told you, Wronskian is not 0 most of the time. But you need to show that. For example, let's say that these were the solutions, the one that we did it. How can we check the Wronskian of that? We are writing the solutions here. We are taking the derivatives. What is the derivative of e to the minus 2t? Minus e to the minus 2t. Minus 3 e to the minus 3t. And I'm taking the determinant. 2 by 2, it is easy. Multiply this diagonal, minus multiply other diagonal. This diagonal is going to be minus 3 e to the minus 5t. This diagonal, minus, which will be plus 2e to the minus 5t, minus 3 plus 2, minus e to the minus 5t. And as you can see, this is exponential function. So this is not going to be it is not zero anywhere. So your Wronskian is not zero. You can say that they form the fundamental set of your solution, and their linear combination is going to be the general solution of your differential equation. So this is the general set of solution. Y1 and Y2 is the fundamental set of solution. And you need to make sure that Wronskian is not zero. And other than that, solving is the easy part. And in here, I just showed that if you have two exponentials like that, once you take the Wronskian, it will never be zero. So if you have two distinct roots, the Wronskian is never zero, so you can assume that these are gonna form your fundamental set of solution, and you can write your general solution easily as the linear combination of these two like that. Okay, this is just showing you this is not gonna be zero. You can use this method easily. So we talked about the distinct roots. Now we will talk about if we have complex roots. What can we do? Okay. So this is the second order constant coefficient differential equation. We put e to the RT, we found the characteristic equation, and we check the roots, and we saw that this b square minus 4ac is less than 0, which means that square root of negative will be complex number. You know that, and this will bring you the roots alpha plus e mu and lambda plus e mu and lambda plus minus e mu. So these are conjugates of each other. Once you find that, you can write your solution as C1 e to the real part lambda t cosine imaginary part mu t plus C2 e to the lambda t sine mu t. Okay? We are using Euler's equation to be able to write that. So if we have complex roots, we are finding the roots first, and the real part is coming as the power of exponential. Imaginary coefficient is coming as the coefficient inside the cosine and sine. And again, the solution is the linear combination of cosine and sine solutions. Look at that. This is the differential equation. We plugged in e to the RT, so our characteristic equation will be r squared plus r plus 1. Why it says 1? So I think this is wrong. Again, this is my mistake. Sorry. What did I say? It should be like that. I correct it now. There you go. R squared plus r plus 1 is 0. And minus b, which is the coefficient of r, plus or minus b squared 1 minus 2ac, 2 times 1 times 1, 4 over 2a. So if you do that, you will see this is going to be the roots, and this is your r lambda, this is your mu. Then this is going to be coming as the power of the exponential, just as we showed in here, minus e to the minus t over 2. And this will come as inside the cosine and sine, 3t. So this is the general solution. And if you have initial condition, again, you need to apply in here. E to the 0 is 1, cosine 0 is 1, sine 0 is 0. That's why you have only C1 equals 2. Because it is given 2 as an initial condition. And once you take the derivative, plugged in 0, you will see that negative 1 over 2 C1 plus 3 C2 is 8. Just solve these together. Just put it 2 in here. You will see that C2 is going to be 3. And once you plug in inside your general solution, you can find your solution like that. And as you can see, the solution is like decaying oscillations. If you have complex roots, since the solution is going to be formed with exponentials and cosine and sines together, you will see the solutions in that form, the oscillations. Okay. And this is another example. Again, our characteristic equation 16r squared minus 8r plus 145 is 0. And if you solve this one with the quadratic formula, minus b, which is 8, minus 4 square root of b square minus 4ac over 2a, 32. And you will see that the solutions is going to be the complex conjugate of each other, which means that 1 over 4 plus or minus 3i. Which means that our lambda is 1 over 4, our mu is 3. And this is going to go as the power in the exponential. This is going to go as inside the cosine and sine. And this is the general form of our solution. And we need to apply the initial conditions. We plugged in 0. That's why C1 will be just negative 2. We will take the derivative and we will plug in 0 at t and make it equal to 1. And these are the constants. And if you plugged in the constants in the general solution, you will see this is going to be the solution of your initial value problem. Sure, Nazlıcan. This one? Previous one. Previous one is that one? This one? Sorry, let me go out from there. And you can talk. Maybe it will be easier than writing.
About you.
Let me share with you. Okay, I'll share the desktop. Here you go. Is this one?
Yes, this one. We found root of 3 multiply with 1 over 2 for mu, but we write 3 for it.
Oh, yes, that's right. Let me see. So this is, I put this one wrong.
Yeah.
Should be 3. Square root of 3, yeah. Oh, sorry, this is not. This is just a mistake. This should be square root of 3, right?
Okay. Yes. Okay.
It's just a mistake. You can just put the square root of 3. I will update it, okay?
Okay, thank you.
And of course, the solution is going to change a little bit after that. But make sure that you understand the general idea, how you are solving it. That's the important point in here.
Yes, I understand the idea, but because of that mistake, I was lost. I tried to figure it out.
Okay, great.
Thank you.
And what we were saying, in here, as you can see, if you plugged in the constants, the solutions will be the growing oscillations this time. In the previous one, it was like oscillations that are decaying, but this one, it's growing ones. And let's look at that one. Second derivative, and there's y term only, and this is very general mistake. Once you are writing the characteristic equation in this one, in general, you are writing r squared plus 9r. It's not 9r because r is the coefficient of the first derivative. There is no first derivative in that one. It's okay. You know, if you have questions, you can write or you can talk. It doesn't matter, but you can stop me anytime. Again, the characteristic equation for that one will be r squared plus 9 is 0. And once you look at the roots, you know that the roots is going to be plus or minus 3i. And in here, lambda is 0, mu is 3. So e to the 0 will be 1. That's why these are only 1 as a coefficient. We have only cosine and sine as solutions. And once, if you have an initial value and if you apply it, you will see that these are going to be oscillations. These are not growing or decaying because there is no exponential term. If the exponential terms power is positive, it is growing. If the exponential term's power is negative, it is decaying solutions, oscillations you will see as a solution. Okay? And since there is no exponential term in that one, your solutions are just oscillations like that. Okay? And now, what did we say? We said that if we have two distinct roots, our solution is going to be in the form of that one. So we are just writing these roots as the powers of exponential. If we have complex conjugate roots, our solution is in this form, which means that lambda is going to be the power of exponential, mu's are going to be the cosine and sine coefficients, right? And if we have distinct roots, how can we write the solution? Right now we will be talking about that. Again, we are writing the characteristic equation. We are finding the roots, and now we see that we have the two roots but the same. Okay, once b squared minus 4ac is 0, you will see that r1 and r2 is going to be equal to each other, and it's minus b over 2a. And now you can write one solution, e to the minus bt over 2a. So the second one is going to be c2t e to the bta. Okay, so for the second one, you need to put t as a coefficient in front of the exponential. The second solution will be t times e to the r that you find. Okay, this is the general form of the repeated root solution. And if you check the Wronskian of that, you will also see that it's never going to be 0. And these equations is going to form the fundamental set. Here you go. This is just one example. Once you write the characteristic equation, this is r squared plus 4r plus 4 equals 0. And if you factor it out, you will see that this is the same as r plus 2 squared. So you have r equals negative 2 as a repeated root. So one of the solution will be e to the minus 2t, another one be t times e to the minus 2t. And the general solution is going to be the linear combinations of these two solutions. Again, to be able to use the initial condition, you need to plug it in here, 0, 0. This is going to be when t is 0, you have only c1, and take the derivative, put it 0, you can find c1 and c2, and you can find your general solution, and the solutions is like distinct root ones, okay, like polynomial ones. And this is another one. If you write your characteristic equation, r squared minus r plus 0.25 is 0, and this is r minus 1 over 2 squared, and r is equal to 1 over 2 is the repeated root. So one solution is e to the t over 2, because 1 over 2 is the coefficient. Another one is t times e to the t over 2. Apply the initial conditions, find c1 and c2, plugged in, and this is going to be the solution form for your differential equation. So do you understand that? Okay, great. So you can have not distinct root. If you have distinct root, you are just writing as the powers of exponentials and put it as a general solution as linear combinations. You can have complex conjugates. Lambdas are coming as the power of exponential. Mu's are coming as cosine and sine. And you can have repeated roots. One solution will be e to the r1t, another one will be t times e to the r1t. That's it. Then other part is just applying the initial conditions. It is much more easier than maybe the first order one, right? You just need to remember what kind of solutions you have. You will just apply the initial values. That's it. This part. And how you can draw this in MATLAB, let me show you shortly. If you open MATLAB, let's see that. plotting, to be able to plot a function is important. For any function or for any data, if you can see how it behaves, can give you a good idea. Okay, that one. We need just the comment window. And let's take one function, this one. 2 times e to the t over 2, or anything. Let's say this one or that one, doesn't matter. You can turn this one as a data where what was the t, for example, t is from 0 to 4, right? T is from 0 to 4, 0 to 4, and let's give an increment, 0.1, okay? And let's define our function f, and you can define this one as a function with an inline comment, and inline is used like that, 2 times e to the t over 2, 2 times, times exponential t over 2, and what was the other part? Minus 2 over 3, minus 2 over 3 times t times e to the t over 2. Now, since t is given as a vector, I put dot before the multiplication because I want to do element-wise multiplication between t and this exponential t's. Because this is going to be a vector, this is going to be a vector, and I don't want vector multiplication. I want element-wise multiplication, which means that multiply first element of t with the first element of exponential. That's why I am putting dot in there. And if you say plot t versus f of t, it will give you this plot. And as you can see, this is the same plot with that one. And it is passing through 2. And this is going to be the plot for yourself. You can play with that plot easily. You can change the color of this one, like R dotted. And if you say yes, it will be the dotted one with red. I said put red. Okay, R was red. And you can put X label, Y label, title. You can make your plot better. Okay. And if you write head plot, you will see all kind of different versions for plotting. Where is that? For example, R is red, G is green. These are how you put, if you want to point out data, these are the styles of data. These are the styles of lines. So you can use them by just changing it in here. No, you will not do in the midterm or final. Just for you to understand what kind of solutions you can get with as a solution, solution of differential equations, to get an idea. But I will not ask you to graph them. I will just ask you to solve them. Okay. So this is just for if you want to see your solution by just typing these 3 lines, you can see your solution easily in MATLAB or Octave or whatever you use as a MATLAB program. Okay. So do you have a question? I will not continue with the nth order, higher order ones. Where is that? Something. Yeah, I'm sharing this. Oh. MATLAB? I can share if you want the MATLAB, but it is gonna be inside the video. I'm sharing the video. And inside that it is easy. Okay. I can save this command window and I can share that here. Okay. And Excel. Would you like to update your Excel on LMS? What do you mean? Olbey, you can say Turkish.
Teacher, we had some wrong on the exam. Sorry, on the Excel, like C1 plus C2 equals to 1, but it must be 2, for example.
So you are saying the PowerPoint slides?
Yeah, PowerPoint. Sorry, my bad.
Yeah, okay. Yeah, I will update that.
Okay.
Okay. And yes, on LMS2, I need to delete that and I need to, put this one back. But make sure that you are solving by yourself. I can have this kind of typing mistakes. Make sure that you understand the idea and solve by yourself. Our exams gonna be online or not certain yet. These are gonna be online. We cannot, ask you to come here. At least for the midterm, we have in 10th of November. I will make it online through MyLab, the program you bought. Okay. There will be a time restriction. You need to start. The system is going to open at that time and the system is going to be closed once the time is up. And you need to send me your written solutions. I will not give you a grade according to the results there. I will give your grade according to your written notes. You need to send me back as one file. You need to take the photos of your written answers, or you can scan them, whatever you want. Put it in one Word file or one PDF file, and you need to send me back with your name. And I will check your answers. Okay, great. I did not take attendance. Let me take attendance. There you go. Okay. Do you have a question? Okay, so you know that Thursday there is the 29th of October. There it is a vacation. We will not have a class on Thursday. I will see you on next week, next Tuesday. Okay, ask Semih.
Hocam iyi akşamlar.
İyi akşamlar.
Ya ben bu kitap konusunda bir şey soracaktım da size. Ben geçtiğimiz hafta sonu size e-mail atmıştım, hatırlarsınız.
Bu kadar çok e-mail geliyor ki bazılarını yapabiliyorum. Tekrar cevap vermezsen bana tekrar atın. Muhtemelen çok e-mailin arasında kaybolmuş demek.
Ya şöyle özetleyeyim hocam ben. Ben siparişimi verdim Çağlayan Kitabevi'nden kitap adına. Ama Çağlayan Kitabevi'nden bana herhangi bir faturalandırma veya da herhangi bir bilgi gelmedi. Daha sonra telefonla ulaşmaya çalıştım. Ulaşamadım. E-mail attım iletişim adreslerine. Oradan da herhangi bir cevap alamadım. Yani sipariş numaramı falan verdiler. Ödemem de tamamlandı ama ben hem kitap hem kod şeklinde almıştım.
Tamam. Kimdi Mehmet? Mehmet Bey miydi? Mehmet Ucuk. Şurada mehmet@çağlayan.com. Lütfen buna mail atar mısın? Beni de CC'le. Tamam mı?
Tamam hocam.
Semih o yardımcı oluyor. Muhtemelen sana da gelmiştir ama sen görmemişsindir. Genel öyle bir sorun var. Çünkü size faturayla beraber mi dedi, maille beraber mi? Bir tane geliyormuş galiba. O gelenin içerisinde varmış o kod.
Ya doğrudur hocam da ya ben sipariş ettikten sonra sipariş numaramın altında şey yazıyordu. Sipariş bilgileri e-mail adresinize iletilecek yazıyordu ama hiçbir şekilde bir şey iletilmedi yani. Benim elimde şu an kod da yok. Giremiyorum da.
O zaman sen o Mehmet Çağlayan oraya gönderirsen.
Tamam hocam. Ben sizi de etiketlerim. E-mail'e gönderirim.
Ben Çağlayan'la konuştum da şimdi bu kitap artı kod almayın dedi bana. Bu sizin değil dedi. O sizin attığınız sadece kod olan var ya 150 TL olan.
Evet.
Sadece onu alın bana dedi. Yani onları siparişi sadece sizin yani bizim okulun adına vermişler. Kitap artı kod olanı almayın dediler bana.
Allah Allah. Yani belki ellerinde yok muhtemelen. Getirtemeyecekler. Öyle o yüzden söylemiş olabilir. Yoksa aynı kitap aslında ama.
Kodlar sipariş olarak veriliyormuş galiba. O yüzden dedi bizim mesela sizin attığınız linkte ISBN Ant'la başlıyor. Onlar bizimmiş. Yani bize özel sipariş bizim okula.
Ya biz sadece diyoruz ki şu kadar öğrenci bekliyoruz. Ona o kadar kitabı hazır edin bize ki sorun çıkartmayalım. Yani sorun yaşamayalım diyoruz. Belki ona göre şey alıyorlar onlar da. Öncesinden sipariş giriyorlar dediğiniz gibi olabilir.
Ya peki hocam biz ödeme
alacak varsa da hani şey almasın diye şey yaptım ben.
Bir şey sorayım o zaman. Biz ödeme yaptık kitaba. Yani belirli bir miktar